Okay, let's start. Do you have any questions? Okay. So last time we were discussing the Ito integral as an object. As a random variable with the following properties, that first of all is a random variable whose first moment, whose mean is always 0, and whose variance, right, which is the second moment because the first moment is 0, and whose variance is this expression, which is a Riemann integral. And second, right, when we know that this is a deterministic function, so roughly, it only depends on time. If we have this, then we know more. We know that our Ito integral, we have a normal distribution would mean 0 and variance determined by Riemann integral against the square of the f, the integrand f. All right. And so after giving examples and things like that here, what we did was we want to, okay, given a function. All right. So let me make it easy for now. Let's say a function of, let's say only, well, okay, let's just do it more general. Given a function of time and Brownian motion, all right, think about stock. Our stock model is exactly a function of time and Brownian motion. We want to express, okay, this function itself as its value, right, at 0 plus something in terms of the Riemann integral and something else in terms of the Ito integral. Okay. So think of this, all right? This is very much to when you have a function only in time, then it's going to be its value at 0 plus, right? In this case, we know what it is. It's derivative in time, integrate, okay? And so if you compare this and this, is exactly this formula when you take away the Brownian motion component. Or if you want, what we're looking for is generalization of the fundamental theorem of calculus, okay? We're looking for a generalization of the fundamental theorem of calculus in the case where now Brownian motion is involved. And the reason why it is beyond the scope of the fundamental theorem of calculus is because the Brownian motion is not differential in time. All right. Now, roughly speaking, you can cast this whole thing as a function of time. Why? Because this is time and this is also time. So all in all, this is just a process in time. So you can cast it like this. Except this makes no sense when you have a Brownian motion component involved, because Brownian motion, again, is not differential in time. All right. So we need to have a separate component reserved for the Brownian motion. All right. So, I mean, if you want, right, this is one extreme when you only have time, okay? You take the Brownian motion away. When you have the only Brownian motion, Now, this is just an example like this. And as you see, if we make the example more general, it will be a little bit more difficult. But right, if you have only Brownian motion, then it's going to be its Brownian motion value at 0 plus, right, just 1 times the change. Okay, and this is by definition. So there's nothing surprising here. All right. One more thing is, right, notice the link, right, between this and this is differentiating. So in some sense, we are looking at, right, or, right, so also has the idea of differentiation, okay? Now, differentiation in quote, because again, right, we're not differentiating anything here because the Brownian motion is a very rough object in time. But what we're saying is, like, if you want to make it precise, more precisely, all right, more precisely, we are stating, or we will be stating, the differential of whatever this object is, okay, in terms of the differential in time and the differential in the Brownian motion, okay? Why? Because if we know how its change is in respect to time and Brownian motion, then all you have to do is to integrate, right? All you have to do is to add things up. Then you will recover this version, all right, as we discussed last time. So in other words, right, one thing to keep in mind is these two versions, 1 and 2, are equivalent, okay? It's almost like saying knowing a function and knowing its antiderivative is almost the same thing. Okay, like, I mean, knowing f prime of t is t, and knowing f is t squared over 2 plus c is one and the same thing. I mean, this is very routine for you, you know, because it becomes formulaic. You don't even think about it. But, right, this is basically the same idea, but because something new, you don't know what object that fits into what, it becomes a little bit strange. But at the heart of it, right, the idea of relating derivative and the integral is just that. Okay. Any questions so far? All right. So, okay, what do we want to do next? So let's just jump right in, okay? So let's do the easy exam, the easy case, and then we're gonna make it, you know, more general later on. So for now, let's drop the time component. Let's just consider a function purely of Brownian motion, okay? So I drop the time component. I only look at the Brownian motion. So this, now I will require, okay? We require that the first and the second derivative exists. And, you know, should be continuous, blah, 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 okay? We won't go into the technical detail because we're more interested in the formula, the calculus of it. So the analysis we're not gonna talk about, but, you know, you must have at least second derivative and then possibly something else. Anyway, if this is the case, then Ito's formula, okay, which is exactly applying, trying to find the derivative of this, or finding the differential of this, will be, the differential will be f prime, okay, of wt dwt plus 1/2 f double prime dt. Okay, so there you go. This is as promised, meaning we're saying the differential of the function we have two components, right? The dt component is associated with the second derivative of the function, 1/2. The dwt is associated with the first derivative. All right. Now, this also implies that f of wt minus f of w0, by the way, right, it's just at this is 0. Or let me do this, okay? Let me do it more generally. For s less than t, this will be the integral from s to t of f prime wu dwu plus the integral 1/2 f double prime of wu du. Okay. We will explain why this is true, what that means, etc. right, soon. For now, we want to apply this to several examples that would illustrate, okay, the formula for you. Any question? Yeah, you take whatever function it is, differentiate twice, plug in the Brownian motion, of course with 1/2, then you got the dt term. Let me give you an example, all right? Suppose we look at wt squared, the square of the Brownian motion. Then what is the change of the Brownian motion square? It will be, right, differentiating. By the way, right, so when I write this, you should look at as f of x is equal to x squared. Okay? Then clearly, right, f prime is 2x and f double prime is 2. So therefore, this will be 2wt dwt plus dt. Is 1/2 times 2, so that's 1. All right. Any question? In terms of representation, right? Another in terms of the integral version will say wt squared, right, minus w0 squared is equal to 2 ws dws plus t. Or, right, because again, this guy's always 0, we got wt squared minus t. Now, the constant, right, can go in and out of the regular integral. Same thing applies here. The constant goes in and out of the Ito integral. So this is 2 ws dws. Okay. So of course, I mean, look, right, I have reason to do so, but let's just keep it like this for now. So this is more of the goal, right? The wt integral and the dt integral. Any question? Now, the reason why I wrote the other thing is because of this. I want to, so basically, coincidentally, this also gives you this identity that this particular Ito integral will be wt squared minus t over 2. Okay. Now, well, why do I bring this up? Well, remember, right, the mysterious properties that we listed above for the Ito integral. Expectations always 0, variance always this, blah blah blah. Okay, now we have an explicit representation. By the way, right, I hope you appreciate this. Is almost like you can say, the integral of t e to a t is, I don't know, right? T e to a t minus e to t or something. So an explicit representation of an integral as a function, that's what you love, okay? Of course, we can live and work with the integral, all right? But once in a while, when we get explicit representation, we can test certain idea, right? And make sure that our understanding of the integral is correct as it should be. In other words, right, let's test that the expectation is 0. What is the expectation? All right. What's the expectation of the Brownian motion square? Well, Wt is normal 0t. That means variance of Wt, which is expectation of Wt square, right? Minus expectation square of Wt is t. But this guy is 0. Therefore, this is t. Therefore, this is 0. As promised, right? I mean, nothing new here if you trust the rule. But again, right, before I guess I tell you the rule, roughly some, I don't know, intuition, but here is an explicit calculation for this explicit integral, which leaves nothing to doubt. Oh, there's something to doubt, right? The Ito integral, but the Ito formula. But if you, I guess here, right, you see everything is consistent. All right. Let's try one more. This one requires a little bit more of knowledge of probability, but the variance, right? What is the variance? We stated, right? So first of all, according to the identity, it'll be this. Okay. Which, right, I hope you know that, sorry, over 2. That, first of all, subtracting, right, adding a constant does not change variance. So you can ignore this term. 1/2 goes out as 1/4. What about the variance of Wt squared? Okay, what is that? Well, here's something for you, right? You may be familiar, or you should be familiar with the object of if you have a standard normal, okay? If you take the standard normal and square, it becomes a random variable that's very popular in statistics called the chi-square. This is the simplest chi-square you can get, chi-square with 1 degree of freedom, okay? And the chi-square has expectation 1. The variance of the chi-square, which is roughly the object we're interested in, will be, of course, expectation of the square, right? Minus the square of the expectation. Well, a chi-square is standard normal square. So chi-square square is standard normal to a 4th. And here is obviously nothing but standard normal square. Standard normal square has expectation a second moment equals to 1, exactly by this kind of argument. Standard normal to a 4th is something some of you know, some of you don't know. We'll have more to say about this soon. This is 3 minus 1, so the answer is 2. Okay? So in other words, the variance of standard normal square, or the variance of chi-square with 1 degree of freedom, is 2. What does that have to do with this here? Well, Brownian motion is normal 0t. So if you divide, if you right, if you divide it by square root of t, right, which is, sorry, right, which, right, if you divide this by square root of t, right, this is exactly like square root of t times a standard normal. Okay, so wt, right, and which is, of course, this is wt. So in other words, instead of calculating the variance of wt squared, right, I can do 1/4, right, variance of square root of t times standard normal square, sorry, like that, which, right, gives me 1/4 variance of t standard normal square. T goes out to be a t square. Variance of standard normal square, as we just showed, is 2. So I got t squared over 2. Okay? What the heck did I just do? What the heck did I just do? What I just did was to take, right, the calculation, okay, of the explicit representation of this Ito integral and calculate its variance using the explicit representation. The reason why it took so long was because, right, I took a detour on, explaining something about the normal distribution. But the final answer is t squared over 2. The goal is to compare it, right, with the other way I told you, right? This way right here. So let's see, right? Well, the other way will say the variance is the integral of w squared ds. But we have done this calculation before, right? This is just s. Where was it? Anyway, right? This is just the variance of ws, so it's just s. So this is 0 to t s ds, which you see easily is t squared over 2. Right? And the two answers match. Okay? Again, demonstrating the consistency of all the formulas I'm telling you, right? Notice when I told you this, right, you're in the dark about what this object is, but you still get this answer. For this particular, right, integral, by applying Ito's formula, we got this explicit representation, and we can test it explicitly, and the answers match. Okay? Any question? Finally, I have this property right here. And I emphasized to you at that time that it must be deterministic for that to be true. Well, so we can ask the question, right? Is this normal? Well, let's see, right? What is it? We have the explicit representation right here. So the integral is wt squared minus t over 2. Well, what distribution does this have? Or in other words, does this look like a normal distribution to you? The answer is absolutely not, because this expression right here is bigger than or equal to minus t. So the whole thing is bigger than or equal to minus t over 2. The normal, right? If it's truly normal, it must be from minus infinity to infinity. Or if you care to say more, remember, right? Wt square is related to a chi-square distribution. So there's no way it can be normal. So the answer, of course, is no. Okay? And again, it's consistent because the integrand here is not deterministic. All right? Question? Okay, so let's do another example. Let's suppose now we look at the exponential function. The exponential function, all right? What is the Ito formula, okay? Apply Ito formula. This is the routine keyword now. Apply Ito's formula, okay? So in other words, differentiate it, find the derivative, that kind of stuff, right? In Calc 1, we give you a bunch of functions. Differentiate this, differentiate that, right? In this context, it's not correct to say differentiation, so we say apply Ito's formula, all right, to it. So what is it? Well, so again, right, when you're not used to this, try to identify the function. The function is e to the x. Okay, again, let's remind you of the Ito's formula. The function differentiating, the function differentiating twice. And so here, right, nothing interesting happens. They're both like that. So in other words, right, this will be e to wt dwt plus 1/2 e to wt dt. Is that okay? So sorry, right? Maybe I should do this. Or right now, if you want to write in the differential, in the integral form, is e to wt minus, okay, e to w0, which is e to 0, is the integral e to ws dws plus 1/2 e to ws ds. In other words, the representation, right, of this function is 1 plus this Ito integral plus this stochastic, this Riemann integral, like that. Any question? Okay. So you can continue, right, to apply this to many things you want, as long as, right, you have to pick a function that has first and second derivative. So if you want, you can do something like, I don't know, the cosine of wt, the wt to cube, you know, the 1 over wt, that kind of thing, all right? So you have, you know, tons of opportunities to explore this on the homework. what I want to do next is to explain a little bit on the Ito formula, all right, on right here, what is going on, okay? So some explanation of the Ito formula. So what is it, right, that we're looking for? We're given a function and we want to find this. Now, this object will look so mysterious until you try to understand what it means. What this object is nothing but a small change in the function as time changes a little bit. As time moves on, okay, the Brownian motion will change, which causes the change in the function, and we capture that by that notation. So if we can understand what this object is, we will understand what this is. Okay, how do we understand this object? Well, you understand this, if you will, right, by, you know, first order. If you remember, they have something called first in calculus one, first order approximation, or they call it linear approximation, where you will learn something like this: f of x plus delta is approximately f of x plus f prime of x times delta. Okay, remember something like that? Or, and then second order approximation is going to be f of x plus delta is approximately f of x plus f prime delta plus 1/2 f double prime delta square. You start to see the familiarity between this and the Ito formula. Okay, so what's going on, right? We will apply the second order approximation, or by the way, this is called the Taylor expansion. All right, around x. We will apply, okay, the Taylor expansion on FWT, where WT will play the role of x. And the kicker is, right, delta here is not this guy, it's not h, but delta is a change in the Brownian motion. Okay, in other words, f of wt plus h, right, is f of wt plus h minus wt. I think this move, right, this kind of trick has been done before, right, when we do conditional expectation. Here it is again. In other words, right, we split, right, the future into the present plus the change. Okay, so, right, again, this will play the role of x, this will be the role of delta. So if you apply the first order approximation, sorry, the second, you get this will be approximately f of wt, because that's x, plus f prime, right, times the change plus 1/2 f double prime times the change squared. And so you understand, right, that what's left to do is let this time goes to 0. Let that time goes to 0. Okay? Because if you do that, then this becomes a differential proper. So in other words, right, bring this over here, you get dfwt, right, is f prime. This obviously become dw. Yeah. All right, what about this guy? For now, right, let's just write like this, even though you know what's going on. Let's see, plus 1/2 f double prime dwt square, right? All right. Now, what is this object then? Have we ever discussed something like that before? We did. All right. Remember, at one point I wrote something like this: dwt square is equal to dt square is equal to 0, in connection, right, to discussing how the path of the Brown motion is very rough. It's so rough that if you square it and you add it up, you still obtain something, right? I think the lecture last week, at some point, we discussed something like this. If you chop the interval from 0 to t to so many, sub-intervals, and then you add the change of the Brown motion up and square them first, right? Then as you chop that up and you add, you will get t out of, right, the whole thing. That's why the change is dt. On the other hand, if you add, right, ti plus 1 minus ti square, you'll get 0. Okay. In fact, you add anything that's higher power than 1, you will get 0. This fact will be important to us to explain if you ask questions. All right. Again, right, this is very, very natural. Where does that come from? Just remember and think of it, right, as each of these guys, let's say if it's equal length, then that's t over n. Okay. Then basically you're adding, right, t over n raised to 1 plus epsilon. But adding a bunch of equal pieces is like multiply by n. And you see what's going on. This and this cancel, leaving you with, and of course that goes to 0 because epsilon is positive. Okay. So we capture, right, this first fact by saying dwt squared is dt. The second fact like this, or if you will, okay. So because of this, right, any dt to any higher power than t is also 0. Sorry, higher than 2. Sorry, right, higher than 2 is also 0. This explains why, if you look at this and you are thinking about it, you should ask, okay, second order approximation is cool. Why don't we do more? Why don't we do third order approximation and things like that? Well, the reason is you could, but when you push time to zero, you will not detect anything because right, the next one will be a cube power, and right, that will switch right the change in the Brown motion to zero. So all in all, what you get is this, which is the Ito's formula. Any question? Okay, so before we move on, all right, let's do some more application of the Ito's formula, but in a fun way, all right? So I'll use, I mean, by application, I mean, it's just a fun trick, all right? Now, like I said, many people, right, if you have a standard normal, I guess anyone should know that its second moment is 1. Not many knows that the fourth moment is 3, or not many keeps this fact in mind. And then when you ask for a sixth moment, I think most people don't have an idea. All right. Does anyone know what the sixth moment of the standard normal is? Well, it is 5 times 3 times 1. And I think by now you will be able to guess what the generic formula is. And so, right, this even has a notation. It's called the, I think the double cumulant or the cumulant or something. It has 2 exclamation mark. All right. Is probably right reminding you of the factorial, right? The factorial just multiply like this, all the way down to 1. I suppose, right, the double cumulant or whatever it is, sort of like say skip 2, right? That's two exclamation for that. Anyway, right? Now that I tell you this fact, do you know why that is true? Can you be confident that this is true? Right? How many ways you have to show that this is true, right? So I think the most painful way, right, is to work with the density function of the normal distribution. I suspect it can be done. I don't know, but that I definitely don't want to touch that. A semi-painful way maybe is by moment generating function. Okay. Now, I'm not here to tell you either one of these because they belong to a probability class proper. What I'm telling you here is a fun way to obtain this fact using the tool that we just discussed, which is the Ito's formula. Okay. How so? Well, how so is, right, that I have shown, right, that Remember what we did with the square. If I apply Ito's formula on the square, I got this, right? And then plus dt. So in other words, I got Wt squared is okay. So relying on the fact, right? Now we kind of switch gear. We rely on the fact that this has zero expectation, okay? Before we checked it. Now we accept this as a fact. If you accept this, then expectation of Wt squared is t. Okay? Which, right, I hope, because Wt squared, right? Always remember that Wt has this relation with the standard normal. Is square root t times the standard normal. This is consistent with, right, expectation of t squared times the standard normal. Sorry. Is t, right? T times the standard normal square. Or, right, that's, that's this guy right here. That's nothing new, okay? But we're just gonna want to start from the beginning again. How do I want to obtain this? Well, let's do round motion to a fourth. Well, what do I get? What I get is 4 Wt cubed dWt plus 2 Wt squared dt. Not 2, 6. Right, because it's 4 times 3 over 2. You bring the 3 down, and that's a 1/2. Any question here? So, right, Wt to a fourth is the integral, right, from 0 to t of 4 Ws cubed dWs plus 6, right, Wt squared dt. Okay, so what's expectation of Wt to a fourth? Expectation of Wt to a fourth then is, this is 0, right? So I got only 6 expectation of this. Remember how I told you about you can exchange the expectation and integration if you're integrating in a Riemann sense. If this is a Riemann integral, right, then you can exchange. So in other words, this is, sorry, 6, right? Well, now you can say that you're bootstrapping on your previous case when you know what this is. So in other words, it will be, but if you check, this is exactly 3t squared. Okay? But again, remember, right, this relation. So in other words, this is expectation of, right, t squared z to a fourth is 3t squared, or expectation of z to a fourth is 3. Okay. Any question? Let's try one more. What about the 6? For a 6th power, right? You see, we should get 5 times 3 times 1, or 15. All right. Well, sorry. First, I should start with Ito's formula, right? Wt to a 6, the change will be 6 dWt. And then you got 30 divided by 2, which is 15, right? That's your 15. Wt to a 4th dt. Okay. Now what do? We represent now Wt to a 6 as a Ito integral and a Riemann integral. We take expectation on both sides. This goes away. This, we pass the expectation inside. Well, what do we see, right? Now we, again, right, bootstrap on our previous result, where this is 3t squared. So in other words, right, this should be 3s squared. Okay, which you see exactly is, right, integrated, you got s cubed over 3, 15t cubed. All right. And of course, right, I don't have to remind you, but this is exactly t cubed z to 6 is 15t cubed, or z to 6 is 15. Okay, and you can just repeat this exercise, and the more mathematically minded in you will be able to prove some kind of inductive, right, induction formula that shows in general that this procedure can be used to show, right, what we claim right here, right, in general. So sorry, this is not z double factorial, right? That's I guess 7. Oh yeah, that's 7. My 7 looks like z. Any question? So try to pay attention and see what makes things work right here besides just some kind of magic trick, maybe using Ito's formula. The underlying theme, okay, in here is that when you use Ito's formula, you reduce your expression that involve Brownian motion, which is like the normal distribution, into something with a lower power. And the assumption is, of course, you know how to handle the lower power, right? So for example, here you just get 1. Here you got w squared, which you know how to handle from before. Here you got w4th, again, you know how to handle from before, so on and so forth. Okay. So this exercise literally, right, demonstrates that Ito's formula is a differentiating formula. Okay, it's a differentiating formula. That the whole idea of differentiating is you tend to get simpler function when you differentiate. Of course, tend to maybe let's be more precise. With the polynomial, right, when you differentiate, you get a lower power. So because of that, right, we say that's simpler. But at least that's true for the polynomial. Question. All right. So the last one I want to do, right, in this procedure is exactly the moment generating function idea. And this one we can do directly. So I have used so many times, we have talked about and used so many times that, sorry, expectation of e to wt, right, is e to exponential e to 1/2 t, right? Even more, we have say this. All right, and this is used directly in the stock in the Black-Scholes, in the Black-Scholes model, right? In the Black-Scholes model, we use this exactly directly. And I did say once upon a time that this comes from moment generating function. You just know it. We did some calculation, right, from the density to show why this is true. Now let's show another way using Ito's formula. Okay, so let's even do this to show you, right, how it comes out. If I say apply Ito's formula, right, to e to sigma wt, okay, what do I get? So d of e to sigma wt is, so what's the function, right? If you're not used to this, try to identify the function separately. The function is e to sigma x. Okay, because the bar motion is always our object, that's the x. So the derivative, right, is sigma e to sigma x. The second derivative is sigma square e to sigma x. Okay, so the Ito's formula will go like sigma e to sigma wt dwt plus 1/2 sigma square e to sigma wt dt. Okay, so you can write this, right, in terms of the integral form like this. Okay. Now, we're interested in this expectation, so we'll take expectation on both sides. This is 1, right? And I guess here you should realize you're in a bit of a dilemma. Because of course this is the object you want to calculate, but it also appears on this side. So how do you calculate it, right? Do appreciate, right? Exactly before, when you apply Ito's formula, right, things get simpler, right? Things get simpler. It gets to a lower power. But exactly, right, by the nature of the exponential, it is not going anywhere. in terms of the power, right? The exponential, you differentiate, you get the exponential back. And that's why you get the same thing on both sides. So it's not direct. But on the other hand, actually, this could be viewed as some kind of blessing if you want. Because sure, you don't get an explicit calculation, but you get something like an equation, right? An equation basically is just some relation that ties, the same thing to each other, right? To itself. So notice that exactly this guy, right, or this right-hand side, left-hand side, is a particular value of the right-hand side at t. What I'm saying is this, if you view this as a function of time, then what you get is f of t is 1 plus 1/2 f of s ds. Well, have you seen this anywhere before? The answer is yes, you have, in a differential equation class. All right, if any of you have taken differential equation, which I think you should have, then this is it. Because what this says is the derivative of f is 1/2 sigma square f of t. Or if you want, differential equation says y prime is 1/2 sigma square y. Plus the initial condition at time 0, right? If you plug 0 in, the integral from 0 to 0 is 0, so this is 1. Okay, or y of 0 is 1. So it all boils down to you knowing how to solve this differential equation, which again, right, if you recall, this is y prime equals to ky. The solution is y is a constant e to kt. All right, and what is that constant? That constant is your initial condition. So here, right, the answer is f of t or y, whatever, right? F of t should, y of t should be 1 e to 1/2 sigma square t, right? That's okay. And that's exactly what I claimed. All right. Any question? So again, right, the purpose of this exercise is just to connect, the function, right, and its derivative, where the function involves a prime motion, or rather the purpose of the Ito's formula, right, it's just that. Now, let's go to the second version of the Ito's integral, right? So to remind you, we were discussing case 1, where the function itself only depends on prime motion. Then we got this. Now, what we want is we want to throw in a dependence on t. Okay, so we have an extra dependence now. And in this case, right, the standard assumption is we say f is C12. This is a notation that you'll see in, like a partial differential equation class, that kind of thing. This one here refers to the t variable. The 2 refers to the w variable or the x variable, right? So here you should look at f as f of tx. where basically it says it's one time differentiable in t, two times or twice differentiable in x, and after you differentiate, the derivative should be continuous. All right. So technical condition, you don't have to really worry about that. Most of the examples we give will be in that sense anyway. So if we have that, right? So what this means is this, that the partial with respect to t, right? So the notation I'll be using, right, is a partial with respect to t, the partial with respect to x, the second partial with respect to x, all exist and are continuous. So I can differentiate up to this many times if I want. If that's the case, then the differential of this guy will be the partial with respect to t dt, right? I do realize, that sometimes what I write here is the value of t, right? Like w sub t, right? When in this context, all right, it really means this, okay? It does not mean f evaluate at t, because there's a Bragg motion here as well, okay? And then f sub x dwt plus 1/2 f sub xx dt. Okay. Now, what in the world is going on? What in the world is going on is actually, you see, this is a generalization of that. Before, when we have one variable, we say it's prime. When we have two variables, we need to differentiate, right? That's why we say x and a prime, second derivative, and double prime. Okay, so this and that are exactly the same thing. What do we get extra? We get the extra t term. I hope it's intuitive. Then we differentiate with respect to it and multiply with a change in time to get the approximation in that direction. Any question? Yeah, all right, Dearling, right? So it's this. I don't know. I mean, once upon a time, right? I think some of my friends would like to do this, but I find it a little bit kind of too much. But they like to do this to demonstrate the idea that, what is it? When you have a function, then it's just like a container, right? Whatever you put in there doesn't matter. Okay. So when I do x here, right, what I mean is that's the second location, right? It's a container. And so when I do, right, I put wt as the value in that container. Now, so you realize, right, when I differentiate here, I differentiate not with respect to time, but I differentiate with the change in this value, which is x. Yes? Now, I think some of the students before did ask a question, and I think for that matter, if you want to write that, I have no issue. But I do think it's a bit awkward to write that. And so, this just demonstrates the idea of container. Same, right, as, I've been doing this so far in the class. Say, right here, right? I say x, and I do this, and I do f prime, and I do f double prime, right? I mean, I could have done f sub x here, no? Okay, it's the idea that I'm differentiating with respect to that container. Okay, but so if you want to write this, that's fine, but I'm not so sure it's a standard notation. I understand what you mean. You want to use that. Any other question? So let's give you example, right? Suppose it's TWT. Okay. Then what do we get? Right, the differential of this. Okay, so do notice, right? Here, what I mean is the differential operator applying to this function. If you're not careful and if you read this superficially, you might see something like this, which may be this. Okay, so in other words, pay attention to the context. All right. So like I said, I always write the differential at the end of the equation. I never write differential before a term. So even if this is the case, the understanding should be differential of this one. Okay. So you should respect that notation to make yourself right. I mean, not confused when you operate under this. All right. This really means you take the Brown motion value times the change in time. This is a change of this function as time changes a little bit. Okay. So none of that. Anyway, this will be, right? So what is f of tx? If you're not used to it, it's just t times x. So the partial respect to t is x, which is wt. The partial respect to x is t. And the partial respect to x twice is 0. So that's your answer. In the integral notation, we get or, simply okay. I hope you saw that what I just did is something like a product rule. It's roughly saying a b prime is a prime b plus b prime a. But of course, right, it's more sophisticated than that. But you can roughly look at this as a version of the product rule. Okay. Any question? Now let's take a look at, right, our Black-Scholes model. We're almost there. We have almost a tool to handle the Black-Scholes model. So let's say it's this. Okay. So now you see, right, from the Ito point of view or from the mathematical point of view, the Black-Scholes model just simply a function of t and wt. Just like this. So it's susceptible to a treatment of the Ito's formula. Or I can find a change, all right, in the stock price. Well, what is it? Again, what is my function? My function is S0 is a constant, all right, is a constant. Eta mu t plus sigma times x. Okay. So first, right, what do? I differentiate in t, then differentiate in x, twice in x. So differentiate in t, right, gives me So, okay, let me do this. There's a trick here. If you do it enough, you see. If you differentiate in t, you see all you do is you bring the mu down, right? You bring the mu down. Everything else is the same. So I could say this, f of t is mu times f. Yes? F sub x is sigma times f. F sub xx is sigma squared times f. Are you okay here? All right, thank you, Dylan. So here, right, then dst will be, should not be surprising you to say dst mu st dt plus, right, sigma st dwt plus 1/2 sigma square st dt, where, right, clearly by the f, right, when you plug in twt, I get s. That's why I plug in like that. Okay, or if you want, I can spell out for you. This is nothing but ftwt. Or, right, I hope you notice something strange. If I pull everything together, I get this. So to capture the punchline, right, this is, say, you know, before I usually always say something like this is a fudging of the details, so something is not quite right. Something not quite right is exactly this term right here, when I go from here to here. If you have this, then you must have a plus 1/2 sigma square in your differential. Or in other words, if your differential is like this, or, right, you know, this is your return. This is your percentage return. Okay, then ST must be emphasis on the minus here, because, you know, and, right, I'm just gonna do this. We'll have a chance to do it more next time. The log return will be mu minus 1/2, like that, coming straight from here, which we talked about a little bit last time. So we'll do it more in more details. But notice, right, I kept saying at one point that the percentage return is higher than the log return, for real, okay? So here's the Edo's formula that exactly demonstrates how that happens, okay? And so, yes, you can go and check, and I think, right, they will do an example of that in homework this week or last week, right? If you have the same stock price, if you report the percentage return, it seems like you're doing better than if you report a log return, okay? And here's the math to back that up, okay? All right, I think it's a good place to stop here, and we'll continue next time. Any question? You too.